Hey, hope you're doing well. In this video, I want to talk about a related rates problem that deals with pouring water into a cup. So here's the scenario. There's a lot I've already written, but I'm going to go through each piece with you. So I'm going to be pouring water into a cone-shaped cup. And what do I know about this cup? The height of the cup is 10 centimeters. The top radius is going to be 3 centimeters. And the water, well, how fast am I pouring the water in? Well, the water is going to be added at 5 cubic centimeters per second. My question is, how fast is the depth of the water changing when the depth is 4 centimeters? So what I'd like to do is envision the water in the cup. The top of the water forms a circle. That's going to have a radius, and it's also going to have a height. Now, I'm not going to put numbers in here. I know I want to do this when the depth of the water is 4 centimeters. But when I'm adding water into this cup, is the depth going to change as the water gets added? Well, yeah. So I do not want to put a number there. How do I relate R and H and volume? Well, that's where this comes in. The volume of a cone is 1/3 of the base, well, pi r squared times the height. Since this is a related rates problem, we could do this with two variables here and start taking derivatives, but I suggest we don't do that. One thing I want to do is I want to take this picture and I want to look at a cross section of it. I want to chop it straight down. What I wind up getting is two triangles, and they are similar. The top radius, the height of the water, the radius of the water. Well, what do similar triangles say? It says that the ratio of corresponding sides are equal to each other. So if I take a height divided by a height is going to be equal to a radius divided by a radius. So I wind up getting this particular equality here. What I can do is I can solve for R in this problem. Now, why am I solving for R? Because the question is asking about how fast is the water level rising. So I want to eliminate R from my problem. So really quickly, R is equal to 3/10 H. So I'm going to take this and plug it into this particular volume formula. So my volume formula becomes 1/3 pi 3/10H squared times H. Now I'm going to do a little bit of algebra here. My volume is 1/3 pi 9/100 H cubed. And I can do a little bit better than this. 9 divided by 3 is 3. I'm going to write this as 3 pi over 100 H cubed. So my volume is equal to 3 pi over 100 times H cubed. Now I'm ready to take derivatives. So this is my model. And the derivative of my model looks like the following. dv dt. Well, that's the derivative of volume, v, with respect to time. 3 pi over 100, that's a constant, so I'm going to leave it as a constant. The derivative of h cubed, I'm going to use the chain rule here. Take the derivative of the outside, leave the inside alone, and then multiply by the derivative of the inside. The last step in all this is to plug in my numbers. dv dt is 5. H is equal to 4. And I have to solve for dH dt. So let me do that really quickly. 5 is equal to 3 pi over 100 times 3 times 16, that's 4 squared, dH dt. So what do we wind up getting at the end of this? Well, we're just solving for dH dt. And this looks like 5 times 100 over 9 times 16. And make sure you don't forget the pi in the denominator. I'm not going to calculate this right now. I'm not going to simplify it right now. You can do that on your own. But the one thing I want to make sure that we do is that I show you the whole problem on the bottom there, is write the units. H is measured in centimeters. Time is measured in seconds. So the units for this is centimeters per second. I hope this was useful. If you have any questions, let me know. Have a great day. Bye.